Hello everyone, my name is Joa and I'm from Rutgers Discovery Informatics Institute. I will present the paper Staging-Based Task Execution for Data-Driven In-Situ Scientific Workflows. This work is collaborated with the Mochi project from the Argonne National Lab. And thanks a lot for the help from all the co-authors and the feedback from all reviewers. Recent research has explored in-situ workflows, that is, in-situ or in-transit data processing, while the data resides in memory on the same system. In the recent work, the term in-situ is typically used to represent a general paradigm that includes different approaches, such as inline or in-transit. In the inline approach illustrated in Figure A, the data consumer, namely the analytics or visualization tasks, share computing resources with the data producer, such as the simulation. In the in-transit approach illustrated in Figure B, the data is transferred to analytics or visualization tasks running on separate resources, usually on the same system, using data middleware services and leveraging high-speed networks, RDMA, or shared memory. For the in-transit approach, if it is the dedicated course of nodes to do the data transfer or pre-processing, these services are called data staging service. As scientific workflows become increasingly data-intensive, it is essential that the mapping and execution of in-situ workflows be data-driven, and enabling in-situ tasks to be controlled and scheduled flexibly based on the data content or the pattern detected from the data values. For the data-driven approach, large analysis and visualization tasks are conditioned by the presence of features in the data whose detection is relatively cheap compared with the actual analysis. There are several benefits for the data-driven approaches. Tasks are controlled based on the patterns detected from the data and user-defined requirements and description for the pattern. The execution sequence in workflow are driven by the data properties rather than being a static or predefined. Tasks are triggered when it is necessary. There are less data transfer. Only the necessary data is stored and processed by the subsequent tasks. What if we combine the data-driven approach with the in-situ approach? How the workflow will look like? There are three typical cases. For the Figure A, feature detection is performed in line after each iteration, and it also uses the simulation's computing resources. When interesting data is detected, the subsequent tasks is also executed in line. The time-consuming analytics or visualization is only executed when it is necessary in this case. In the in-transit approach illustrated in Figure B, feature detection is performed in line, but the data is then transferred to the analytic or visualization task running on separate resources when interesting data is detected. While a staging area may be used by the data middleware in this approach, it does not execute the analytic or visualization tasks. In an alternative in-transit approach, feature detection is performed by a data staging server, as illustrated in Figure 3. The data produced by the simulation is entirely transferred to a staging server. The feature detection is performed in the data staging area. In order to evaluate the model presented in this work, we also need to provide solutions for each data-driven in-situ approaches discussed in this paper. There are existing works to support the inline in-situ, such as the Catalyst or Alpine frameworks. There are all kinds of data staging frameworks that support the in-transit data transfer. But for the in-staging data execution, it is not fully explored, since it is complicated to execute tasks in data staging service based on the redistributed data. We need to provide a flexible execution engine and the index solution for the in-staging data. In this work, we also present a framework that focus on flexible in-staging data execution based on the methods used in previous data staging surveys. With the mathematical model and all kinds of in-situ data-driven solutions, we evaluate the model and show that choosing the proper in-situ data-driven solution can decrease the workflow execution time significantly. Let's start to discuss about the mathematical model presented in this paper. Equations at the right side are the specific model correspond with the particular approach. We have three approaches and three models here. We will go through the first two equations briefly and discuss the third one in details. There are detailed explanations about every parameters used in the equation in the paper. The goal of the model is to show the workflow execution time and how it relates with the key parameters of the workflow settings. For the first one, there is only one component. The total workflow execution time equals to the simulation time plus the detection time and the time to execute the analytic and visualization tasks. For the second one, there are two components. One is data producer and another is data consumer. The workflow execution time equals to the maximum value of these two components. Let's look at the third case in detail, the in-transit in-situ with in-staging feature detection. The first component is the simulation. So the time to compute the simulation equals to the n times s plus p. N represents the number of the iteration. S represents the time to compute the simulation for each iteration, and the p represents the time to put the data into the data staging service. The second term is the data staging service. The data staging service can process the in-staging data detection after the data is put into the data staging area. The extra time spent on the data staging service is W, G, and D in the equation. The term W represents the time to wait for the available resources to get the data from the simulation. The term G represents the time to get the extra data from the simulation, and the term D represents the time to process the extra in-staging data detection. The last component is the analytic or visualization task. One important parameter is the NL. It represents the index of the last iteration that generates the interesting data for the simulation. The term WGD represents the time to wait, get, and process the in-staging detection for this data in data staging service. And the WGA represents the time to wait, get, and process the actual analytic or visualization tasks for this data. Therefore, the total workflow execution time in this case depends on the longest one among those three components. With the mathematical model for each case, theoretically speaking, if we could know the workflow settings and key parameters used in the model, we can anticipate the execution time for different approach and choose the preferred one before running the workflow. In order to evaluate the model to test if it can anticipate the workflow execution time, we also need to prepare the implementations of the different in-situ data-driven approach and use these approaches to implement the workflow. In order to evaluate the mathematical model, we need to construct the workflow based on these three approaches. For the first two approaches, we could use existing solutions. For the third one, there are some challenges. For example, how to index the data in data staging area and get the partition which needs to be processed, and how to describe multiple in-staging executions with the user-defined conditions. Besides, when the data satisfies the user-defined requirements, how to notify the consumer such as the analytic or visualization task, and let them to get the data and process the data. This figure shows the data flow and the control flow between the producer and consumer. The data staging service used here is a solution presented in this paper for the in-staging execution. In particular, Multiple servers can start in parallel, and the data produced by the data source, such as a simulation, can be written and buffered into the bulk data manager of a particular server. The address manager can find all available running servers and select one among them using a round-robin strategy. The metadata manager is responsible for storing the meta information, such as the variable name and the spatial information, which are used to index the raw data. Upon updating the metadata, the trigger manager checks if there are related user-defined task triggers. Then the in-staging execution are started asynchronously to check the properties of the raw data. If the data satisfies the requirements defined in a trigger, an event is written into the event queue associated with the corresponding triggers. For the data consumer, triggers can be registered with the trigger manager before the simulation starts, and then events will be pulled from the event queue associated with the registered trigger. When there is an event about interesting data, the consumer extracts the meta information from the event. After that, the metadata can be used to index the raw data based on the distributed hash table, and the client fetches the partition of raw data from the bulk manager of corresponding server for further processing. For the communication layer, we use the services provided by the Mochi project at the RPC layer. This figure shows an example of a configuration file for an in-staging task trigger. One task trigger includes several tasks executed at the data staging service. The name of trigger represents the identifier of a specific trigger. In particular, when the metadata in a specific domain is updated, the function with the name checkAverage is executed. This function may check the average value of the raw data located in this domain. The return value of the checkAverage is accessible by the value compare function, which executes a comparison operation. For example, if we are interested in the data with an average value which is larger than a threshold, the threshold value can be set by the item parameter compare. When the value compare returns true, the function VTK_write that outputs the data in VTK format is applied to the corresponding data. All functions specified in triggers can be customized and extended according to different requirements of the workflow. Let's discuss about the evaluation. For the platform, we use the Cori supercomputer. For the data source, we use the Gray-Scott simulation, which is based on a reaction diffusion model. For the data analytics, we use the synthetic analytics with adjustable execution time. For the inline analytics, we just process the data analytics after each simulation iteration. For the data staging service, we use the Gorilla framework presented in this work, which is focused on the in-staging data execution. There are 3 experiments in the evaluation. For the first experiment, we test the scalability and performance of the data staging service. We compare our framework with other data staging solutions and show their performance. For the second experiment, there is a comparison between the inline and in-staging execution. We vary the percentage of the data analytics executed inline and in staging, and then we compare the workflow execution time. For the third experiment, there are comparisons between different data-driven in-situ approaches mentioned in the mathematical model, and we will take more time to discuss the third experiment in details. This is a model for 3 different approaches. One important question is, what parameters should be fixed and what parameters should be varied in the experiment? Since in this experiment, we mainly focus how to compare different solutions for processing the data, so the data source is fixed. The number of iterations and the size of data generated by the simulation is fixed. Let's discuss the varied parameters and how these parameters relate with the important workflow settings. The feature detection time is represented by the parameter D, and the analytic or visualization time is represented by the parameter A. For the percentage of the qualified data, it is related with the Ni and Nl. Ni represent the number of the iteration that generates the interesting data, and Nl represent the index of the last iteration that generates the interesting data. We assume that the interesting data is evenly distributed among all iterations here. For the factors data staging nodes and thread pool size, they are related with the parameter W, P, and G. If we provide more data staging nodes and comparatively large thread pool size, it needs less time for in-staging tasks to wait for the available resource to get and process the data. But if there are more threads for processing the in-staging tasks, there are less computing resource will be used to process the data I/O, and the performance of the data put or get, such as parameter P and G, will be influenced. This table shows all factors that we can control before the workflow starts, and we list 3 typical cases for the evaluation. For the case 1, all factors are comparatively low. For the case 2, we increase the analytic and visualization time. For the case 3, all factors are comparatively high. For the table at the right side, we calculate the workflow execution time for different approaches based on the mathematical model, and we also get the preferred approach for different cases. The figure under the table shows the experiment results of the workflow execution time with different data-driven approaches and the workflow configurations. Although there is match between the theoretical value and experimental values in some degree, the accuracy of our methods needs to be improved further. We still need to monitor key parameters during the workflow execution and make decisions about the preferred approach dynamically, instead of anticipating the preferred approach before the workflow starts, since the key parameters may change during the workflow execution. For our conclusions, in this paper, we discuss typical in-situ and data-driven in-situ approaches and provide a mathematical model of performance. We also show that the preferred approach can be anticipated based on in-situ mathematical model and key metrics. Our evaluation indicated that the proper choice of in-situ approaches can reduce the workflow execution time significantly. For the future works, we plan to explore how to monitor key parameters automatically during the workflow execution in different HEC systems. Based on these parameters, the staging framework can make more accurate decisions in real time and even provide more elasticity for resource for in-situ workflows.